Okay, today we're going to talk about metals, metallic structure, and the properties of metals and how that structure relates to those particular properties. So let's remind ourselves what a metal is, or a metallic bond is. A metallic bond is a bond between two metals. So we don't get a metallic bond between a metal and a non-metal. It's only when you have a solid lump of iron that might have other metals in there as well, but generally it's just one metal, right? So the type of structure is considered to be the sea of electrons that we're going to um, uh, understand in a second. And the reason for this C is as a result of this delocalized electrons. Again, we're going to understand that a bit more in a second. Usually solid. There is one example of a liquid metal, which I'll leave you to put in the comments for extra points. And generally it's a very high melting point. It's never soluble in water, conductive, malleable, ductile, and lustrous. So the sea of electrons. Here you can see the individual cation metal cations, right? And floating in amongst all of these cations are these electrons. Now, the electrons aren't in particular orbits. They're not going around in one particular pattern. They're flying through randomly, right? And the reason for that is because the attraction between the metal cation and the electron is so weak that it's just as likely to be here as here, as here, as here, as here, as here, as here, as here. Right? So it's not being tightly held, so it drifts fairly cleanly from cation to cation. As a result, it can conduct heat really quite easily, right? They're able to conduct kinetic energy because as a heat source starts here, and these um, electrons start vibrating and moving fast, they start to heat this bit very easily and start heating this bit very easily because these excited electrons can move freely from one end to the other. Imagine if these electrons were only around this bit, as they became excited, they would still just say excited here, and that would move very slowly from one section to another. All right, so that's why the sea of electrons results in a high conductivity of heat. The same principle is why there's a high conductivity of electricity. As electrons are added to this side, we think that's basically what electricity is. If we put a battery over here and connect electricity here, more electrons are added here. Well, these electrons flow very easily from one side of this metal lattice to the other to complete some kind of circuit. So that's why this sea of electrons and the free delocalized electrons is why the metals conduct electricity very easily. Malleability and ductility. Um, uh, we're going to compare metals with ionic compounds here for a second. It's nice to kind of see these metal cations like we showed before and these sea of electrons. I think in a previous video I described it as like it could almost be seen as like a gluey goop holding everything together. The um, the electrons don't care if they're in this nice little pattern, or they don't care if they've been rearranged by some kind of incredible force pushing them down there. They don't care what arrangement these cations are. They're being held together by this glue, this sea of electrons that can float very, very easily from one area to the next. Compare that to an ionic lattice, which is held together through the series of negative ions and positive ions, and negative ions want to align perfectly with positive ions, right? Because negative and like forces repel, don't they? Right? So negative is going to attract to the positive, which is attracted to the negative, which is attracted to the negative, right? Well, if you then apply force, then all of a sudden all these would move down, and negative is next to the negative, and the positive is next to the positive, and why that flies apart. Now that's just to kind of compare. That's ionic, is why they'd repel, but with the metallic it doesn't matter. So this is why, whether it's malleable or ductile, this sea of electrons acts as this, gluey goop that holds it all together. So we can bend it into any kind of arrangement. And here's the same idea presented again. Yeah, we can see that the doesn't matter where these cations are. It's the gluey electron soup that holds it all together. High melting point. That means that the bonds are very strong. The bonds are very strong because there's a lot of attractive force between these cations. And in fact, what you'll notice is with group 1 metals that have one valence electron, their strength is weaker than something with 3 or 4 valence electrons, right? Those metals have a lot more electrons in that electron sea to hold these cations together. But the cations are held together by these electrons, regardless of how many there are. So generally, they have a very high melting point. They're relatively highly packed because the lattices can be very closely stacked. There's not a lot of repulsion going on. These electrons again can ensure that there's not going to be any holes that kind of appear as a result of weird ionic forces going on, as you tend to see with ionic compounds. With metals, because we don't care where the metals are, you don't tend to have these kind of pockets developing. And that's all there is for today. The structure of metals. Now, the most important thing is when you are asked for the the properties of a metal, don't just list them. Don't just tell me a definition of them. You need to tell me how, referencing the sea of electrons, how that sea of electrons causes that property. That's the kind of answer I'm looking for when I'm asking for the properties of metals. Have a go at the question, and good luck.